What's up, everybody? This next video lesson is going to be discussing ionic bonding. We're going to talk about all that you need to know about ionic bonding, what it is, how it happens, and how to create formulas. First, let's talk about what are some characteristics of ionic bonding. First of all, ionic bonding is a metal bonded with a nonmetal. We know that metals are those substances on the left side of the periodic table, including the alkali metals and the alkaline earth metals, but also the transition metals. Those would be mixed with one of the elements from the right side of the periodic table, something from group 17 or group 16 or even group 15. Now, why do ionic bonds form? Well, there's this rule in nature called the octet rule, in which it says all atoms are stable when they have 8 electrons in their outer energy level. So a nonmetal, which maybe has 7 valence electrons, doesn't necessarily want an electron. We talked about this in a previous video lesson. There's no desire to have electrons. What it really wants is stability. And so stability rules in this case. So what a nonmetal will do, it'll gain electrons in order to gain a full, stable valence electron shell. Now, where does it get those electrons from? Well, it must get them from something that wants to, or I should correct myself, is more stable when it gets rid of its electrons. And those elements would be metals. Let's take, for example, a few drawings down here. Sodium, neutral, is a 1s2, 2s2, 2p6, 3s1. Now, that electron in the 3s1 is unstable, and the only way to make it more stable would be to add 7 electrons in order to achieve the octet. And the octet means it has 8 electrons in the highest energy level. Or what it could do is unlock a trapped octet underneath its outermost energy level. And that's what it's easiest to do. It's easiest to get rid of its electron on the outside, and what it does is it opens up an energy level on the inside, and this sodium atom now becomes a sodium +1 ion. Now, where does that electron go? Well, it goes to an element that would be more stable by filling its outside energy level, in this case, chlorine. Chlorine's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5, and as you can see here, there is only 7 electrons in this third energy level, and chlorine would be more stable if it gained that electron, and sodium would be more stable if it lost that electron. And so when chlorine gains an electron that was given up by sodium, it now has a negative charge. And what happens is those electrostatic attractions begin to form between the cations, the positive ion, and the negative ions, the chlorine ion, to create what we call an ionic bond. Here's another look at an illustration that represents the same thing that I just showed you on the last slide. We've got sodium with its 1 electron that is unstable, and if it loses its electron, it opens up a stable inner core energy level. So it removes its electron or loses its electron for stability's sake onto chlorine, which is almost a full energy level, and it would become more stable if it gained 1 electron. Now those atoms turn into ions, and they then attract one another because of their oppositely charged particles. But this doesn't always happen in a 1 electron to 1 electron lost and 1 electron gained sort of scenario. Sometimes an ion might have 2 electrons that are in its highest most energy level. And by losing those 2 electrons in that high energy level, like in calcium's case, it would unlock an s2p6 electron configuration underneath. But only thing available for that calcium is a chlorine, which can only take 1 electron each. So it loses 1 electron to 1 chlorine and 1 electron to a different chlorine. And as a result, this combination of metal and nonmetal, or cation and anions, is a 2-to-1 ratio. So electron transfer ratios, meaning that both elements need to become stable in order for the compound to form, doesn't always happen in a 1-to-1 ratio. Sometimes it's a 1 cation for every 2 anion ratio, or maybe sometimes it's a 3 cation for every 1 anion ratio. So what you need to do is pay close attention to how many valence electrons the cation has and how many electrons the anion has, and determine how each of them can be satisfied by removing the electrons from the cation and gaining electrons in the anion's case. Now, for this particular example, because calcium lost 2 electrons and chlorine gained 1 for each ion, then the ratio is Ca Cl2. Now, what would the ratio be between aluminum bonded to oxygen? First, we have to think about how many valence electrons each one of these particles has. And aluminum has 3 valence electrons, and oxygen has 2. So if aluminum lost all 3 of its valence electrons, well, oxygen can only pick up 2, so it would have a remaining valence electron that would be unaccounted for. And so what if we then double my aluminum? So instead of having 3 valence electrons, we now have 6 valence electrons to place. And now we can think, well, if each oxygen can take 2 of those, then maybe I can do 3 of those oxygens in order to eat up the 6 electrons that aluminum is trying to give away. Now, the number of electrons lost always has to equal the same number of electrons gained. And once we figure out how many electrons are lost and how many atoms are losing, we can figure out how many electrons and how many atoms of that are gaining. And so in this example, 2 aluminums would be needed to lose 3 electrons each, that's 6 total electrons lost, and 3 oxygens would be needed to pick up those 6 electrons because each oxygen can take 2 electrons. And so the formula turns out to be Al2O3. Now I'd like to show you a little trick here that you can use to figure out how the formulas are going to form when you're talking about different ions and their combinations. Let's take, for example, these two. One is a metal, sodium, and the other is a nonmetal, nitrogen. And I think, what are the charges of each of these if we can predict their charge based on their position on the periodic table, which was something that we learned about in a previous video lesson? Well, since sodium is an alkali metal, it has a +1 charge when it ionizes, and when nitrogen is an ion, it becomes a -3 charge. And so I predict the charge of the ions, and then watch what I do next. I take the number of the cation and place it as the quantity of the anion, and I take the charge of the anion and make it the number of the cation, and what results is an Na3N combination, and that is the exact combination of +1 charge ions, because think about it, 3 sodiums each at +1 charge are equal to 1 nitrogen each at -3 charge, because the plus charges and the minus charges always have to cancel each other out. This is known as electroneutrality. Sometimes I refer to this as the crisscross method, because you take the charge of one and cross it with the charge of the other one to figure out the formula. And that works about 95% of the time. But there are certain few cases where that doesn't work, and I'll talk about those next. What happens if I have 2 ions? One is calcium, which is a +2 charge ion because of its position on the periodic table, and oxygen is a -2 charge based on its position on the periodic table. And if I crisscross these two to form an ionic compound, what we get is Ca2O2. And for the novice, that looks like there's nothing wrong with that. But in fact, there is something wrong with that. Because what we know about ionic substances is that if you have the ions, they always reduce to their lowest ratio. So if you've got 2 calciums and 2 oxygens, well, you can divide them both by the same number, and they reduce to 1 to 1. So that is the situation, the 5% of the time, where when you crisscross the charges, you don't get the final answer because the amount of each ion are not in their most reduced ratio. Now we're going to practice writing the formulas for these ionic compounds. And using the information from the first video lesson earlier in this chapter, you should be able to predict the charge of each one of the ions in the pairings and then come up with the lowest ratio of ions in order to form the proper chemical formula. So let's take a look first at this beginning one, this lithium with fluorine. Lithium's an alkali metal and they're +1 charge, and fluorine's a halogen and they're -1 charge. So if you take and crisscross lithium +1 and fluorine -1, then you get lithium fluoride. And this is easy because one's a +1 and one's a -1, so they easily cancel each other out. Now let's take a look at this next one. Magnesium, because it's an alkaline earth metal, is a +2, and nitrogen is a -3. This one is a particularly tricky one. It's one of the more difficult ones that you'll come across. But basically what you want to do is find the lowest common multiple of 2 and 3 in order to multiply both of these numbers by so that they're equal. Or you could do the crisscross. But thinking 2 and 3, the lowest common multiple is 6. So if I multiply magnesium 3 times plus 2 is 6. And if I multiply nitrogen 2 times negative 3 is negative 6, then we've got electroneutrality, right? We've got plus 6 and minus 6 charges cancel each other out. So in the end, you'll have Mg3N2. Now this next one with aluminum, which is a plus 3 charge, because group 13s, at least above the metalloid line, are plus 3 charge. Below the metalloid line, they might have a plus 1 or a plus 3 charge, but aluminum's above the line. Now bromine's a halogen, and they're always negative 1. So if you crisscross these charges, or you find the lowest common multiple of 3 and 1, which is 3, well, you multiply this by 1 to get, multiply this by 3 to get 3, then you've got electroneutrality. So when you write it out, it should be AlBr3. This next one, calcium's a plus 2 charge and oxygen's a minus 2 charge based on their positions on the periodic table. Now this is one of those examples that I showed you on the last page where if you crisscross the charges, you're not going to get the most reduced ratio because you're going to have Ca2O2. But we're all pretty smart in math, I hope anyway, that these reduce to 1 and 1, so the final answer is CaO. In this next one, since hydrogen is listed first, we're always going to put the metal or the cation first. So this is one where hydrogen is acting as a plus 1 charge, and nitrogen, because of its position on the periodic table, is acting as a negative 3 charge. And if you crisscross the charges or find the lowest common multiple and figure out the right ratio, what you get is H3N. Now this last one's a bit tricky because tin is underneath the metalloid line, and underneath the metalloid line they could have 2 possible charges, which is why if you ever have a metal underneath that line, you'll have to be told what charge you want to use in order to create that ionic substance. In this case, I'm telling you, I want you to use the plus 4 charge ion of tin. So tin's a plus 4 charge, and oxygen, because of its position on the table, is a minus 2 charge. And when you crisscross the charges, when you take the 2 and put it on the tin, and you take the 4 and put it on the oxygen, what you get is SN2O4. And some people will just write that down and walk away from that. But remember, with the same situation as the CaO situation, is that if it can be reduced or divided by the same number, then you should reduce it to the lowest ratio. And this is an example where you should reduce it to the lowest ratio. And so SN2O4 should be reduced to SNO2. And that is how you write ionic formulas given the charges, combining them in the lowest ratio in order to reduce the charges so that you achieve electroneutrality. Ionic substances form these network of crystals known as a lattice or a crystal lattice. And we write the formula for an ionic compound such as sodium chloride as NaCl, and it on paper looks like there's just one sodium and one chlorine that is in that particular substance. And in a manner speaking, you're right. But ionic substances don't just identify themselves as individual packages of sodium and chlorine, but rather they form these crystal lattices of alternating sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine. And they repeat this pattern over and over and over again. Because if you think about it, a sodium can be bonded to a chlorine because they're opposite charges, but that chlorine is just kind of hanging out in space, and there's a negative charge which is available for other positive charge ions to be attracted to it. And so it's not like because it's bonded to one sodium, it loses its negative charge. It just simply cancels it out when we're talking about formulas, but when we're talking about actual ions, they maintain their ionic charge all the time, and it's available to then ionically bond to another crystal of sodium chloride. And so they form these repeating patterns known as crystal lattices. And in fact, this is one of the distinguishing characteristics of ionic solids, is that they can always look at under a microscope, you can see their crystalline structure. Oftentimes they have flat surfaces and sharp corners because that's the way the crystal develops in the microscopic level. Here is another way in 3 dimensions to look at sodium chloride, and you'll see the alternating sodium, chlorine, sodium, chlorine, sodium, chlorine. But if you count up all the sodiums and all the chlorines in that crystal lattice, it'll always be in a 1-to-1 ratio, which is why we write the ionic formula for ionic substances in their most reduced ratio. Now there's a couple of other examples of some crystalline solids down here. We have sodium chloride now in a 3rd way, but there's another one called calcite, and then this one, this white one, has some yellow with white in it. That's just another crystalline structure that we might come across. And this is primarily why we don't call ionic compounds molecules, because molecules imply an individual packet, And we talked about this in a previous video lesson, in a previous chapter, about how molecules are kind of defined as an individual packet, like water. Like a molecule of water, here's one molecule of water, and you can separate it from the other molecules of water, and they don't necessarily interact with each other on the microscopic level. That's not true, but more on that in the future chemistry lesson. But that's why we don't call ionic substances molecules. Rather, we call them crystal lattices, or we use a generic term called a compound. They form repeating patterns of their formula, so they don't just stand alone as individual packets. Now we're going to talk about a couple of unique properties that make ionic compounds different than other type of compounds in chemistry. And the first thing I want to talk about is their hardness and how brittle they are. Because these positives and negatives kind of line up opposite, positive, negative, positive, negative, positive, negative, it forms a very strong bond. In fact, it's the strongest type of bond, which is a common misconception in chemistry. Some people think other types of bonds are the strongest bonds, but indeed ionic compounds take the most energy in order to break the bonds. It also results in very hard and very brittle substances. Now, what does brittle mean? That means when it breaks, it kind of cracks sharp corners and flat edges. And here's how this works. When you slam an ionic substance with a hammer, you're basically forcing half of this crystal lattice in a downward direction. These two columns essentially shift down one. And when it does that, then you have positives lined up next to positives and negatives lined up next to negatives. So you see how this shifted down a little bit. And now those similar charges repel each other, and what you get is a clean release from one ion to the other. And so these are pushing away from each other, pushing away, and the crystal cracks. But what you'll notice is that it's a nice, often flat or fairly flat, clean break. It's not jagged, it's nice and flat, which is what it means to be brittle. Another property of ionic substances is that they can conduct electricity when they're in their liquid state or when they're dissolved in water in what we call a solution. But they cannot conduct electricity when they are solid. Now, what does it mean to be a liquid ionic compound? Well, as you might expect, if we want to make something a liquid, we need to heat it up. But because ionic compounds have the strongest types of bonds, this requires the most amount of heat in order to turn it from a solid to a liquid. Imagine melting snow from snow into liquid water. Well, this is melting solid sodium chloride crystals into liquid sodium chloride crystals. We need to reach temperatures approaching 801 degrees Celsius in order for this to happen. Now, those are temperatures that not even your oven at home can approach. And so it is very, very, very unlikely that you will ever see liquid molten ionic substances. Rather, you will see solutions where an ionic substance has been dissolved into water. Now, you might be asking yourself, why does it matter whether or not it's solid or liquid or molten, or even solution? Well, thinking about this, if you're trying to get electricity to flow through a substance, you need to be able to have ions that can move, which basically passes the electrical current or the electrons from one side to the other. And when a solid ionic substance, they're alternating positive, negative, positive, negative, positive, negative. And that does not mean that the electricity can flow. In fact, ionic solids make very good insulators of electricity until you melt them, and then they make great conductors of electricity. But rather, when you melt ionic substances or dissolve them into water, those ions have the ability to move free of one another. They're kind of sloshing past and sliding past one another. And when you begin to pass an electric current through molten or aqueous solution, what you get is the positive ions that can kind of flow in the direction of the negative terminal of the electricity source, and the negative ions can kind of flow in the positive direction of the electricity source. And because of this freedom of movement of the ions in their liquid or aqueous state, this is how and why they can conduct electricity. Another property that we want to talk about is how ionic compounds dissolve into water. And this picture does a really good job of explaining how this happens. Now, what happens when you put salt or any sort of ionic substance into water that can dissolve? What happens is that the crystals in the solid form are always represented by a positive and negative ion. They are always showing their positive and negative charge. Well, water comes in and bumps into the edges and the corners and the sides of the sodium chloride crystal. We'll use sodium chloride in this example, but this is true of all ionic substances. But the water comes in and bumps into the positive particle of the sodium chloride lattice, and it surrounds it, as you can see, with its water molecules and carries it away one particle at a time. This is why when we dissolve things into water, it appears as though they disappear. But what really happening is that the ionic crystal is being broken up in pieces that are too small to see. Once the sodium's positive is pulled away, then we've got a couple of negatives that are available, and the water comes in and surrounds each one of those ions. And eventually, you can't dissolve any more solid substances into water because basically all the waters are busy holding each one of the ions individually. And at that point, you can't dissolve anymore. But we'll talk more about that in an entirely different chapter known as solutions. But for now, what we want you to know is that when you put a solid into water, it breaks up into its individual ions so that you can't see it because each one is too small to see with the naked eye. But this is why, when it's dissolved, it can conduct electricity in water. Finally, the last property that we're going to talk about for ionic compounds is the melting point. And melting point is basically the temperature at which it's turning from solid to liquid. And the melting points of ionic substances are incredibly high compared to things that are not ionic. And the reasons why is because their crystal lattices basically stabilize the entire structure. And in other words, each one of those positive ions is completely surrounded by negative ions. And instead of thinking of them as just like individually bonded, they're really bonded multiple times to each other. And they help each other out and stabilize, and they interlock the strength of the crystal lattice, and it requires more and more energy in order to break those bonds and thus melt the solid ionic crystal. So looking at this table over here, you can see some of the things that are ionic, like cesium bromide has a plus 636, or even magnesium oxide is positive 2,825, and that's in degrees Celsius, everybody. And even sodium chloride has a positive 801. Now, not ionic substances are things that are covalently bonded, are things that have melting temperatures that are at 0 or below. Look at ethanol, negative 114, ammonia, negative 77, hydrogen chloride, negative 114, methane, negative 182. The warmest or hottest temperature of a substance that is melting on this table anyway is water, and you wouldn't expect 0 degrees to be considered something that's particularly warm, but it is indeed pretty warm when you're talking about melting points of things that are not ionic. But in conclusion, ionic substances have super high melting points because their crystal lattices stabilize the entire structure, causing it to require a lot of energy or a lot of heat in order to melt it. Well, that takes care of this video lesson. Thanks for watching.